So we have already discussed up to Kirchhoff's law, and now we will discuss some other topics of the current electricity, that is the combination of cells. That is another part of the current electricity. Previously we have discussed the combination of resistance in series and parallel. Now there are combination of cells. Now let us first consider what is a cell. Cell is a source from which energy is stored in the cell, and this energy is capable of converting in the form of electrical energy. That is called a cell. So energy stored in the cell in any other format other than the electrical format, mostly in the form of chemical energy. Now when this cell uses in a circuit, this energy is converted into electrical energy and producing potential difference across the resistance. Okay. Now the entire energy that is stored in the cell in the form of chemical energy, that cannot be converted into electrical energy, because always there is certain amount of loss when one energy is converted to the other form. So that loss does not mean that there is a violation of the conservation of energy. It converted to some other form, that is mainly heat. So that's why when we use a battery to run a torch for a long time, so when the electrical energy is produced across the filament of the torch bulb, then some part is producing electrical energy, but in the entire process, entire battery, connecting circuits, entire torch setup will be heated up. So this heat energy is the loss actually. So the stored chemical energy inside the cell, one part of it converted into electrical energy, producing potential difference. Another part of it is producing heat energy. Okay, so that is we call loss in energy or lost volt. That is actually called. So it is the potential drop against the internal resistance of the circuit. Internal resistance means whenever you are using a battery, entire body of the battery is heated up. Means inside the battery there are some material through which charges will flow and current will flow, and as a result this material offers some resistance. That is called the internal resistance of the circuit, and due to internal resistance, against the internal resistance there is a heating effect for the flow of current. That is considered as the lost volt, and due to which entire circuit setup is heated up. Clear? So entire chemical energy cannot be converted into electrical. Some heat will be produced, which we considered as a loss in the conversion of the chemical energy to electrical energy, and that is the cause why the circuits when it is in use are heated up. Okay. So this chemical energy which is stored inside the battery is generally termed as EMF. That is called the potential difference in open circuit condition. Open circuit means no current will flow. So at that moment the energy stored in the battery is the EMF. That is one form of chemical energy. Now when the battery is in use, then the circuit is closed, then across the resistance, the external circuit, some electrical energy is produced from this chemical energy. That electrical energy is called the potential difference. Okay, that electrical energy causes the potential difference, and there is a significant loss in the form of heat energy. So that is called the lost volt against the internal resistance of the cell. So normally when we draw this kind of a diagram, we consider just this is an external resistance. You can mostly consider that it's a bulb. Now this is the cell and this small resistance connected in series on this line is called the internal resistance of the cell. It is actually not outside the cell, it is actually inside the cell. This internal resistance is the resistance of the material of the cell. That is actually inside, but in the diagram it is drawn always outside. Now you can consider this external resistance. Suppose a bulb, filament of a bulb, that is capital R, internal resistance is considered as small r. Then if I current flows in this circuit, then I can consider that this capital R and small r are connected in series because same current flows through each of them. Then you can write this E equal to I into R plus R according to Ohm's law. E equal to I into R plus R. You can also say that this can be written as E equal to IR plus I into small r. So this is the stored chemical energy. This one is the I into R, that is the potential difference produced across bulb, which you can measure by inserting a voltmeter in parallel. Because if you insert a voltmeter in parallel, then you measure this potential difference. Okay, so this can be IR can be written as V plus extra. This one is the lost volt, because due to the flow of heat, due to the flow of current, this heat is produced across this resistance also. That is the Joule heating. So Joule heating is not only done here, Joule heating is also done against the internal resistance that is producing the heat energy. So we consider that this electrical energy plus heat energy produced will be equal to chemical energy stored in the battery. Chemical energy stored in the cell or battery. Okay, so this is the total conservation of energy. Now if you want that 100% to be converted to the electrical, then you can consider that the device is not 100% efficient, because it cannot convert entire chemical energy to the electrical form. Some part is lost as heat energy. Okay, now, so which one is greater between EMF and potential difference? This one is EMF, this one is potential difference. So you can consider that chemical energy stored in the cell is EMF, and electrical energy produced across the external resistance is called the potential difference. Now which one is greater, EMF or potential difference? EMF. But you cannot say that EMF is greater than potential difference. You have to mention the condition. See, in this particular case, EMF is greater than potential difference. There is no doubt. Let me tell you another case. Suppose your mobile battery is completely discharged, no charge in the mobile battery, and you connect it with the electrical socket by using the charger for the charging. The energy that is coming from the outlet, electrical outlet, is in the form of electrical energy. Electrical energy means producing potential difference. The energy that is stored in your mobile battery, inside your mobile battery, is in the form of chemical energy, because if you open the battery, it is written on the side of a battery that lithium ion battery. Lithium ion battery means it is stored in an chemical form. Now when you are doing this charging process, the charger, the battery, everything will be heated up. That means some heat energy is produced, means the total electrical energy that is coming from the outlet is not converted inside your battery as chemical energy. Some heat energy is still produced there. Means the potential difference is partially converted into EMF, which is stored in your battery, and remaining part is producing heat energy for the charger, where for the battery entire device will be heated up. So in this case, which one is greater, electrical energy or EMF? That is potential difference or EMF? Potential difference that is coming, that is greater. A part of it is converted inside your battery, that is EMF. So in this particular case, potential difference is greater than EMF. So don't make a comment that EMF is greater than potential difference or potential difference is greater than EMF. This depends on the condition. Now in this case, EMF greater than potential drop when cell is discharging. This is the first point. Second point, potential difference greater than EMF when cell is charging. When the cell is in charging condition, then EMF is small, potential difference is large. First one, you are using the battery, so the longevity of the battery decreases, so battery discharges. So during the discharging of the battery, EMF is higher, potential difference is lower than EMF. But whenever you are recharging, the opposite will occur, potential difference will be higher, EMF will be lower. Okay. Now, see, now let us consider some cells are there. N number of cells we consider. There are n number of cells in this line. Each cell have EMF E and internal resistance small r, and external resistance connected to the circuit is capital R. Okay. Now let us consider in this case, through this R, the current flowing is I. Current flows through the R is I. All the cells are connected in series. All have same EMF, same internal resistance, means identical cell. Then what is I? Because how many cells are there? N. So total EMF means NE in series, and total internal resistance is N into small r. But N into small r can be considered to be in series with capital R. So total resistance of the circuit will be capital R plus N into small r. So total EMF by total resistance will give you the current. Okay. Now, suppose we have one of the cell in a separately, like this. One of such cell is taken separately. EMF E, internal resistance small r, connected across the same external resistor capital R. So it will send current I1. So in that case we can write I1 equal to E by capital R plus small r only for a single cell. Okay. Now we will check two conditions. First one is this one. Internal resistance of the cell is very large compared to the external resistance of the circuit. That is, small r is very large than the capital R. What will happen in this case? See, small r is very large. So with respect to that, capital R is negligible. So this one will become NE by N into small r, because we can put capital R equal to 0. So in that case I will be equal to simply E by small r, because N will cancel and it will be E by small r. So this one reduces to approximately E by small r. What happens to this one? This one also reduces to E by small r. This one also reduced to E by small r. Means, if you have one cell having very high internal resistance than the external resistor, then whatever the current you will get from this cell, if you connect many cells in series, the same current you will found. Means, connecting more cells in series will not be beneficial. For one cell, whatever be the current, for n number of cells, the same current will come. If internal resistance of the cells are very large compared to the external resistance, then it is not advantageous to connect the cells in series. Okay, because current will not increase, same current will flow. For one cell, for 10 cell, same current will flow in this situation. Okay. Now the second situation. If small r is very less than capital R, then what happens? Small r is very small compared to capital R. Then for the first case I can write I equal to N E by capital R, because I put now small r equal to 0. So it will become almost N E by capital R, and for the single cell it will become E by capital R. So what it gives? I is almost N times I1. So single cell, if produces current I1, N number of cells will produce N times more current. So when the internal resistance of the cell is very small compared to the external resistance, then it is always advantageous to connect those cells in series to get high amount of current, because the current will be multiplied by N times. Single cell if delivered I1, 10 cell will deliver 10 I1, but for that you have to ensure that internal resistance is very small compared to external resistors. Okay. So if internal resistance small, to get high current, connect the cells in series, not in parallel, because in parallel current will not increase.
So the combination should be small or just one cell should be small?
Yes, again,
The internal resistance.
internal resistance of every cell, because all are identical cell.
The combinations are?
Combination is also very small. Now, this is the series combination of the cells. Now I will discuss one more point in the series combination. That is, okay, have you written all this? See, they are all identical cells, okay, as shown in this diagram. How many cells are connected? 5. All have internal resistance R and external resistor. All are identical resistors, EMF E and internal resistance small r and external resistance capital R. There are total 5 cells connected. What will be the expression for I? That you have to write. কত? What is the expression for current? Check carefully the diagram. One is connected in opposite order, so you have to take care of that. The middle one is connected in opposite polarity. Is it 40? Check. See? This one is plus E. This one is plus E. This one is minus E. Plus E. plus E. Now add all this algebraically. What it gives? 3E, not 4E. Because if you consider that there are 5 cells and I invert one of them, then it is 5 minus 1. No. 1 inverted means actually 2 is subtracted. See, all the EMF is written, add this. Because one cell that is inverted, that will cancel one more. So remaining will be 1, 2, 3. So 3E will be the effective potential difference. Because this minus E will cancel 1 plus E. So plus minus that will produce 0. Remaining are 3 cells. So it will be, current will be 3E divided by R plus 5R. Now see, for the internal resistance, there is no polarity. So internal resistance will simply add, that is 5R, smaller. External resistance is capital R. So total equivalent resistance of the circuit is capital R plus 5 smaller. But the effective potential, effective EMF, that drops. If one cell is in opposite order, the effective potential EMF drops by 2. Okay, so that's why it will not be 4E, it is 3E. So remember, if there are n number of cells and among them k number of cells are connected in opposite order, there are n cells, suppose n is 20, and k number of cells, suppose 3, are connected in opposite order, then the effective EMF will be n minus 2k into E by R plus NR. This will be the general form. Suppose we consider n number of cells, among them I consider k number of cells are connected in opposite order. In this particular problem, k is 1. So you have to subtract from the original that 2. So if you write for this problem 5 cells are there and 1 of them are connected in opposite order, then 5 minus 2 into E, that is 3E. So this is the general formula. So if you have n, suppose 50 resistance, 50 cells, and among them 6 cells connected in opposite order. So from 50 you have to subtract 2 into 6, that is 12. So these are the effective number of cells. So then you will get the EMF actually. But for the internal resistance there will be no polarity, so internal resistance will remain same. Okay, that is only for the series combination. You have to remember this one, because most of the time if someone says that one resistance is two cells are connected in opposite order, student directly subtract 2. Smaller by n. See, since they are connected in parallel, potential difference across the parallel combination is always same. So total EMF will not increase. It will remain E divided by total resistance R plus, see all this small r, n number of small r internal resistances are connected in parallel. So their equivalent is R by N. So that R by N is in series with the external resistor. R by N. So E divided by capital R plus small r by N. That is the expression for current. Now similarly for a single cell I can write here E R R I1. I1 will be equal to E by R plus R. Now again two conditions we will check. First one, small r is very less than capital R. Tell what happened? What will be the value of I in this condition? Small r is very small, so just put here 0. It will be E by capital R. And what will be I1? It is again E by capital R. So what we will get? I is equal to I1. So when internal resistance is very small compared to the external resistance, there is no advantage in connecting the cells in parallel combination. Previously, in this situation, if you connect in series, then current will increase by n times. But in parallel, current will not at all increase. It will remain same. So what is advantage in series combination is not an advantage in parallel combination, just opposite. The other thing, limit, if you check, which is a disadvantage in series, check here, it will be an advantage. If you consider capital R, small r is very greater than capital R, that is internal resistance is very large. Previously, when internal resistance very large and connect the cells in series, then current will not increase. Now see, in this calculation we will show that current will increase. So now we can put capital R 0, put capital R equal to 0, so I will become E by NE by small r. By putting capital R equal to 0, you can write I equal to N into E by small r, and here by putting capital R equal to 0, you can write I1 equal to E by small r. See, there is n times increase in current. So when internal resistance of the cells are very high, to get maximum current, connect those cells in parallel. When internal resistance is very low, to get maximum current, connect those cells in series. Okay. Now, this one, this is called the mixed combination of the cells. Mixed combination. So what is given? N number of cells, there are many identical cells. Okay, each having EMF E and internal resistance small r. EMF E and internal resistance small r. In a particular column, in a particular row, there are n number of such cells connected in series. In a particular row, there are small n number of such cells connected in series, and there are m number of such rows which are connected in parallel. M number of rows are there and n number of cells in each row, and in this m number of rows are connected in parallel. External resistance is capital R. You have to find the expression for current. First, what we will do, we will calculate the total EMF and total internal resistance of a single row. So let us consider the first row. In the first row, how many cells are connected? N number of cells. So total EMF will be NE and total internal resistance will be NR. Now we can simplify this one and write that is NE NR same, and all such M numbers are connected in parallel. Now, if M number of cells are connected in parallel, then what will be the EMF? Same, NE. Each cell has EMF NE. So M number of cells are connected in parallel. In parallel, potential difference or EMF remain same. So it will remain same. So in the next simplified diagram, we can write that entire EMF will remain same, NE, but internal resistances, that will vary, because NR number of internal, NR is the value of each internal resistance in the second circuit, and how many such resistances are connected in parallel? M numbers. So it will be NR by M, because if there are 4 resistance R connected in parallel, their equivalent will be R by 4. Similarly, here NR is the amount of the resistance and M such number of resistance are connected in parallel. So the equivalent internal resistance will become NR by M. NR by M. So total resistance divided by how many are connected in parallel, divide by that. External resistance is capital R. Now you can simply write the expression for I. I will become NE by R plus NR by M. This is the expression for the current. NE divided by R plus NR by M. Okay. So you have to remember only this last formula for solving the numericals. And one condition you have to remember, that in which setup maximum or in which condition maximum current can be drawn from the cell. The derivation is there in the book, but I will tell you one process to remember. When the external resistance and the internal resistance are equal, equivalent internal resistance are equal, then only maximum current is drawn. Sometimes students believe that if I consider that the internal resistance is 0, then maximum current is drawn. That is not true. If internal resistance and external resistance are equal, then only maximum current can be drawn. That means the relation will be for I max external resistor R should be equal to NR by M, means equivalent internal resistance. Then only maximum current can be drawn. Okay. Okay, see, next we will consider the other cases. One or two problems we will discuss. First one is, let us consider I equal to I naught into 1 minus small t by T naught. I equal to I naught into 1 minus small t by T naught. Okay. Now it is given that I naught equal to 2 ampere and T naught equal to 3 second. T naught equal to 3 second. Okay. Then find the, write down. It is given that current flowing through a resistance is I equal to I naught into 1 minus T by T naught. I naught equal to 2 ampere and T naught is given 3 second. Now find the charge flowing through the circuit. Find the charge flowing through the circuit between 0 to 3 second. Find the charge flowing through the circuit between 0 to 3 second. That you have to find. See, first one is the method that is a straightforward method. Just integrate to find Q, because from that I can write I equal to dq dt, that is equal to I naught minus I naught by T naught, because both are constant, into T. Okay, then write dq equal to I naught dt minus I naught by T naught T dt and integrate. So it is getting from 0 to q, it is from 0 to 3, it is from 0 to 3. Okay, just straightforward integration. So you can write this one as q, this one will be I naught, integration will give you t, limit is from 0 to 3, minus I naught by T naught, this one will give you t square by 2, limit is from 0 to 3. Now put the values. So it will be q equal to I naught is given 2, and then in the bracket it will be 3 minus 0, 3 minus 0 because upper limit 3, lower limit 0, minus I naught is again 2, and T naught is given 3 second. So put that, then after that 3 square by 2, that is 9 by 2 minus 0. Okay, so it will become q equal to 6 minus this 2 and this 2 will cancel, this one cancel and get 3. So it will be 3 coulomb. ইন্টিগ্রেশনে ভুল হয়েছিল, 3 coulomb. What happened? Huh? ও বৃষ্টি আসছে তাই। Okay, little bit earlier small break. Now we will discuss another part, that is the heating effect of current, and finally we will come to the measurement and all these things. Heating effect, a small portion, you have to remember two things. Suppose there is a resistance and we consider that the current flowing through that resistor is R. Current flowing through that resistor is I. Resistance is given R. Current is flowing for a time t second. Then heat will be developed and we can write this H proportional to I square, provided R and T remain constant. Okay, these are the constants. H is proportional to R when I and T remain constant. H proportional to T when I and R remain constant. This law are called Joule's law. It is experimentally derived by Joule. Okay, now H proportional to I square, H proportional to R, H proportional to T, provided something are taken constants. Now if I consider all of them together, then I can write H proportional to I square RT, where which one is constant when we write H proportional to I square RT? Previously, when we write H proportional to I square, then R and T are constant. H proportional to R, I and T constant. Now H proportional to T, I and R constant. Now when we write using compound variation that H proportional to I square RT, then which are constants? No, nothing is constant. Joint variation means when you add them in the joint variation, then all varies. No one is constant now. So from this, by employing a proportionality constant, I can write H equal to I square RT by J. Proportionality constant is taken as 1 by J. 1 by J means J. What is J? Mechanical equivalent of heat. Mechanical equivalent of heat, its value is 4.2 joule per calorie. 4.2 joule per calorie. If you write only I square RT, then you will get the heat energy in the unit calorie. If you write I square RT by J, then you can calculate the equivalent heat energy in the form of joule, in the unit of joule. Means if you write from this JH, that it will be equal to I square RT. Now you know that W equal to JH means if you are doing the work W, the equivalent amount of heat produced is H, then they are related by W equal to JH, that is called Joule's law. So in that case, this JH I can put W, and you can verify many of the formulas previously you have derived. I can write this one in this manner. I square RT can be written as IR into IT. Now what is IR? Potential difference across this resistance. So I can write it is V, and IT is charge flowing through the conductor. So you can also define this, that potential difference equal to work done per unit charge. Because I can write from here V equal to W by Q. The same logic is coming after introducing the constant J. Okay. Now, one more thing you have to be very careful when you are applying Joule's law. Now let us consider that potential difference across this resistor is kept constant. Across this resistor, if potential difference is kept constant, then what will be the form of Joule's law? Means instead of current, you have to deal with potential difference. I will convert from that equation only. See, for this circuit using Ohm's law, I can write V equal to Ri. Then what is I? V by R. I will substitute it directly over there. So H will become 1 by J I square. I square means V square by R square into R into T. Okay. In this circuit, Ohm's law is valid. So I can write V equal to Ri. Now in this equation, in place of I substitute V by R. Because from this Ohm's law I can write I equal to V by R. Okay, I equal to V by R. Just substitute it there. 1 by J is there. In place of I write V square by R square. There is one more R into T. Okay. Now cancel 1 R. And what you get? H equal to 1 by J into V square T by R, means V square T by JR we are getting. Now check from this form, if you try to write Joule's law, you have to write H proportional to V square when R and T are constant, H proportional to 1 by R when V and T are constant, H proportional to T when V and R constant. Okay. The relation with resistance and heat developed will be changed. Previously, when current is constant, H and R are directly proportional. But now when potential difference is constant, H is inversely proportional to R. So this is the only difference. So have to be very careful regarding applying the Joule's law. What is given constant, that you have to identify carefully, that whether potential difference is given constant or current is given constant, because there is no problem in the variation with time, but there is a problem in the variation with resistance. Current constant means resistance and heat are directly proportional. Potential difference constant means resistance and heat are inversely proportional. So accordingly you have to change the form. Okay, clear? Now I will give you one problem. And now see, since we have calculated already W, I can calculate power also. Just from this W equal to I square RT. Okay. Then if you calculate W by T, it will be I square R. So from this relation you can directly write W by T equal to I square R, which is called actually the power. Okay. By using Ohm's law, this form, in this equation you can also write it in the format V square by R or V into I. Any form is correct and you can apply any form to solve the problem. Either I square R, V square by R, V into I, all forms are the form of power. You can apply any one to solve the problem. But remember, which one is given constant, that has to be carefully taken. Okay. Now write down one problem. Two different external resistors, capital R1 and capital R2, are connected with a cell separately. Means the cell is given, first you connect the first resistor R1, then remove this and connect the second resistor R2. It is found that rate of heat developed in both the external resistors are same. It is found that the rate of heat developed in both the external resistors are same, then find the internal resistance of the cell. Then find the internal resistance of the cell. What will be the internal resistance of the cell? That you have to find. What are given in the problem? Only capital R1 and capital R2. So the answer should come in terms of only these two.
These two, but both of them are equal.
No, not equal.
Can be equal, sir? Oh.
Very difficult, na? See how. First you consider the cell. It has some EMF E, internal resistance small r, connected with an external resistor capital R, 1. Okay? Capital R1. Suppose current flowing through this one is I1. Rate of heat developed means actually power. Rate of heat developed same means actually power is same, because from this equation that I have written, H equal to I square RT by J. So rate of heat developed means H by T, that is same. H by T is I square R by J. So H by T same means I square R by J is same. J is a constant for both of them. So only I square R, this part is constant for both the connection. Okay. Now I will only focus on this I square R part. Check. Now for this I will calculate the I1. What is I1? E by R1 plus small r, right? E by R1 plus small r. Similarly, in the second circuit, when second resistor is connected, R2, this is I2. So what is I2? E by R plus R2 plus small r. Is it clear how to write I1 and I2? Now consider that power is same for both the power developed across both the external resistors are same, means rate of heat developed will be same. That is I1 square R1 should be equal to I2 square R2. Power is I square R. So I write for the first circuit I1 square R1, for the second circuit I2 square R2, and that is given equal in the problem. Then first take a square root of both the sides. You will get R1, I1 root R1 equal to I2 root R2. Okay. Then put the value of I1 and I2. Directly put. it will be E by R1 plus R root R1 equal to E by R2 plus R root R2. See, E will cancel from both the sides. Now simplify and find the expression for R. Just cross multiply. If I cross multiply this one, I can write first term will be R2 root R1 plus R root R1 equal to R1 root R2 plus R root R2. See, all of these are coming after cross multiplying both sides. Then all the term containing small r are taken to the, take them to the left. R root R1 minus R root R2, and other terms are on the right. See, okay. Then can I take R common? It will become root R1 minus root R2, and from this what can be taken common? Root R1 R2 can be taken common, this entire thing. Root R2 is already there, and R1 means root over of R1 whole square. So I take common root R1 R2. So what is left here? Root R1. In the second term, what is left? Root R2. Just multiply and you will get these two results. See, if you multiply this term, root R2 will be there, and root R1 into root R1, it will be R1 into root R2. Second term, root R1 will be there, root R2 will be R2. The same term will be there. And R1 and R2 are not equal. So this is your result of the internal resistance. Root over of R1 R2. So if you remember this formula, directly you can solve this problem. Suppose if it is given 3 and 27 or 9 and 81, this type of values are given, directly use this formula root R1 R2 to find the. It is actually the geometric mean of these two values R1 and R2. So internal resistance of the circuit will be just root over of R1 into R2. Very easy formula, just remember this one. Okay. Now, in case of meter bridge is there in the syllabus. If there is meter bridge, The meter bridge principles are similar to it works on the basis of Wheatstone bridge principle, that is on the balanced condition of the Wheatstone bridge. So if the question of meter bridge will come, then directly apply the Wheatstone bridge formula to solve this problem, because Wheatstone bridge formula is given as R1 R2 equal to R3 by R4. Okay. Now generally sometimes student write P by Q equal to R by S, that is also possible. Now in this case, in this R1 plus R2, in the meter bridge there it is taken as 1 meter long wire, and where you tap the key, the jockey, from that portion the resistance is divided according to the length. Resistance is divided according to the length, because meter bridge wire is always taken as equal cross section, uniform cross section, such that area is constant, and you know R equal to rho L by A. So if area is also constant and rho is already constant, so R is directly proportional to length. So if R1 has a length L1, R2 has a length L2, then this L1 by L2 ratio and R1 by R2 ratio, these two are equal. It is matching with R3 by R4, and since it is taken as 100 meter long wire, that means L1 plus L2 together will be 100. So sometimes L is given, then L2 can be written as 100 minus L1. L1 plus L2 is 100, so L2 I can replace by 100 minus L1, that is equal to R1 R3 by R4. Generally R3 is given as a known resistor, then you have to only find out the value of R4, for which the bridge will be in balanced condition. So in this method you can actually find the value of these unknown resistors. The entire length of the wire is 100. If you tap the key at any point, then this portion is R1, this portion is R2. So R1 by R2 will be equal to L1 by L2, because resistance directly proportional to length. Like electrical measuring instruments, potentiometer is not there in the syllabus, only you have to learn the sensitivity formulas and all this for the galvanometer and voltmeter. Now we will discuss another part which is also very difficult, that is magnetism portion, that is electromagnetism portion. So like electrostatics, and it is more conceptual than electrostatics and more confusing also. So I will go little bit slowly, because otherwise you cannot understand anything. First thing is that previously we have discussed the charges at rest, what effect it can produce, that we will discuss. That is the part of electrostatics. Now, if the charges are in motion, then only electric field is not only created by the charges, another field is created. Okay, it has different dimension as that of the electric field, because unit and dimension will not match. It's a separate, completely separate field will be developed. But as long as charge is at rest, it will only produce electrostatic field. This second field is not observed at all if the charges are at rest. As soon as the charge starts moving, it may move with acceleration, it may move with constant velocity, whatever be, it will produce another field. That field is called the magnetic field. So it is solely responsible due to the motion of the charges. If there is no motion of the charges, this second field will not be produced. Okay. Now, first of all, write down this one, such that when you read from any book, you can identify the key points. If the charges are in motion, then apart from the electric field, another field is produced, which is called magnetic field. Okay. Now, what is the origin of magnetic field? Obviously, the motion of the charge. So, moving charge is the origin of magnetic field. Moving charge is the origin of magnetic field. So, in case of a moving charge, I can consider this charge q moving with a velocity v. This one can be considered as a moving charge. Charge in motion, q into v I have done. Now check, what is the origin of electric field? Electrical charge, that is q, that is a scalar quantity. But origin of magnetic field is not a scalar quantity. Q into v. So q into v totally is a vector, because v is a vector quantity, velocity. So q into v itself is a vector. So the origin of magnetic field and electric field differs. Origin of electrostatic field is a scalar quantity. Origin of magnetic field is a vector quantity. Okay. Now, sometimes people earlier days called that this vector is actually a magnetic charge. Magnetic charge is a vector quantity, like electric charge. But today it is completely discovered that there is nothing called magnetic charge. It is the electric charges in motion which produce magnetic effect and magnetic field. Now, if this charge is flowing through a wire, then we can consider it is a current. Moving charge is equal to a current, because charges in motion, they constitute current. So we can as well write that if this charge, first we consider only constant velocity. If it is moving through a distance L, then this velocity can be written as L by T. If the charge particle is moving through a distance L with uniform velocity, then I can write that distance traveled, velocity of the charge particle is L by T. Then what is Q by T? Current. So I can as well write this expression as I into L. Current into length of the wire through which current is flowing. But length of the wire has some direction that is taken in the direction of the current flow. Current is in this direction, so length of the wire is taken as a vector, and the arrowhead over that vector is taken and its direction is defined in the direction of current flow. Then this I into L, this product, is called the current element. Current element. So current element and moving charge both are equivalent. So both can produce magnetic field. So that's why around a current carrying wire you will get magnetic field. If the charge is moving, you can get the magnetic field. If current is flowing through a wire that is similar to the movement of the charge, so around a current carrying wire you will always get a magnetic field. That is experimentally determined by Oersted. That is the Oersted experiment. Okay. So you can write as the origin of magnetism either moving charge or an current element or a current element. Both can be treated as a origin of magnetic field. Because moving charge and current element are basically same. Okay. Now, first we consider that some magnetic field is there and how it is affecting a moving charge. So, though we know that field is more fundamental than force, but what is derived first? Field or force? What is discovered first? Force, concept of force. Then people realize that field is more fundamental, so field has to be determined. So we will follow that chronology. We will discuss the magnetic force first, then we consider that the origin of field is required, so then we will go to the origin of the field. So let us consider first that some magnetic field is present in a region, and in that region a charge is placed, a positive charge is placed in that region. Is there any force felt by this positive charge in this magnetic field? Any magnetic force felt by this charge in the magnetic field? No. If you now think about these two situations, a positive electric charge is placed in an electric field, it will experience force Q into E. Suppose a positive charge is placed in a magnetic field B and it will not feel any magnetic force because this charge is not moving, because magnetic force will only act on the charge if the charge is in motion. Now make an analogy between them. An electric charge can produce electric field. Now if we say that another electric charge is present in that field, then it will experience some force. So what is the origin of that field? If the same type of another thing is placed in the field of the first one, then it will experience force. Okay. So charge is the origin of electric field. So another charge present in that field will experience force. Similarly, what is the origin of magnetic field? Static charge or moving charge? Moving charge. So unless another charge in the magnetic field is in motion, it will not experience any magnetic force. So the charge which is produced, taken as a test charge, that should move in a magnetic field. If it is at rest, then no magnetic force will act on it. Clear? So write down. Since a moving charge can produce a magnetic field, since a moving charge can produce a magnetic field, then another moving charge in that magnetic field can experience magnetic force. Another moving charge in that magnetic field can experience magnetic force. I use the word can. It may not. It cannot in some situation feel no magnetic force. Okay. See how this force is defined. This is called the Lorentz formula. F magnetic, that is equal to QV cross B. This is the formula for magnetic force felt by a moving charge Q in a magnetic field. I consider the velocity of the test charge is V, the amount of charge is small q, and some magnetic field is present there from the beginning, that is considered as B. Then the force on that moving charge is Q into V cross B. It is called the Lorentz formula. Now, clearly you can see if I put V equal to 0, then the charge is at rest and it will not feel any magnetic force. So first condition is that F equal to 0, if V equal to 0. If the particle is at rest, no magnetic force is felt on it. Another, if F equal to 0, if theta equal to 0 degree or 180 degree, because QVB means its magnitude will become QVB sin theta, where theta is the angle between velocity vector and magnetic field vector. VB, this angle is theta. Then sin theta will come in the cross product. So if theta 0, sin theta will be 0. In theta 180, then also sin theta will become 0. And in either case, the magnetic force will be 0. Okay. So I should write here Fm. This one will be 0. Fine. So if this means 0 degree means magnetic field vector and velocity vector of the test charge are parallel to each other or anti-parallel to each other. In this situation, there will be no force. And in which situation the force will be maximum? For 90 degree. Theta 90 means sin theta has the maximum value. So F has its maximum value equal to QVB, and that is possible if theta equal to 90 degree. So if the charge particle is moving perpendicular to the magnetic field, then it will experience maximum magnetic force. Okay. Now what is the direction of this force? Defined by cross product. So it is perpendicular to both V and B. If you remember this cross product, V cross B will show a direction according to the right hand thumb rule. It is showing a direction out of the board. So in this case, I draw it upward. So it is actually out of the board. And if you are going oppositely, then it will be into the board. So magnetic field is defined by V cross B. So you have to remember this right hand rule always. V cross B. Then V cross B, V and B in same plane, then the thumb will show upward. Don't take B cross V. You have to go from V to B. Okay. Now, earlier I mentioned one thing, that whenever we say electric field lines and sometimes we say electric lines of force, I can use any term anywhere. Instead of electric field lines, if I say electric lines of force, there will be no problem. But the same thing in case of magnetism, we cannot. I cannot say magnetic field, instead of magnetic field lines, the word magnetic lines of force. Why? In case of electrostatics, I can always say electric lines of force, electric field lines, both terms are same. There will be no problem. But in case of magnetism, you cannot say magnetic lines of force. The lines that you draw you see in your book, that are the magnetic field lines, not magnetic lines of forces. Magnetic lines of forces are never drawn in the book. Sometimes students write magnetic lines of forces, but that is incorrect. See why. Okay. How electric force is defined on a charged particle? Q into E. I consider Q as the test charge and it is positive. Okay. Then, if it is the direction of the electric field and a charged particle is placed here in this electric field plus Q, then in which direction electric force acts on this charged particle? In the direction of the field, because Fe equal to Qe means F vector and E vector, these two are parallel to each other, means along the same line in this case. So this force vector on this charged particle is along this Fe. So the straight line that you draw for representing the electric fields, the same straight line is also representing electrical force. The lines which representing electric field, the same direction, same line will represent electric force. So write down electric in electrostatics. Force and field are represented by the same line. Force and field on a test charge, force and field are represented by the same line, because force is felt by the test charge and field is created by the source charge, but both are along the same line. Field and force are along the same line. So you can call either field lines or lines of force. There will be no problem because both are representing same line. But think about a situation if they are not representing the same line, then can you say that field lines and forces are equal? These words are equal? No. Now see, it is not true in magnetism, because magnetic force is defined by Fm equal to Qv cross B. Now, what is the angle between Fm and B? Are they along the same line? Just go to the previous diagram. Force Fm and B, they are always perpendicular to each other because defined by cross product. So direction of Fm and direction of B are always different, perpendicular to each other. So the line which represents B cannot represent magnetic force Fm. So in that case, magnetic lines and magnetic force are not the same lines. So you cannot say it. So whenever you will say, you have to say magnetic field lines, because forces are always perpendicular to those lines. Whenever we draw the magnetic lines on the paper and in the book what are given, these are magnetic field lines, means the lines showing B tangent to any point will determine the direction of magnetic field B at that point, not the direction of magnetic force at that point. Clear? Because force is perpendicular to that. If it is parallel like electrostatics, then we can say that it is also representing direction of the forces. But here the tangent will not represent the direction of the force. To a electrostatic field lines, if you draw the tangent at any point, that tangent will determine the direction of field as well as the direction of force. But to a magnetic field lines, if you draw the tangent at any point, it will show the direction of the B, not the direction of Fm. Clear? So write down. In magnetic field, B and Fm are perpendicular to each other. So lines representing B are not same as the lines representing the force. As the lines representing the force. Okay. Lines representing B are not the lines representing the force. Okay. Now, so now from this we will calculate something. First one is, if this force Fm is acting on a moving charge, Q into V cross B, it is acting on a moving charge, and suppose under this action of this force the moving charge is displaced by an amount dr. Moving charge is displaced by an amount dr. So what is the work done? dW, that is equal to Fm dot dr. Fm dot dr. This is the work done, because due to this magnetic force I consider that the charge particle is displaced by an amount dr. So Fm dot dr will give you work done. Now, how to calculate this work done? Can I write this one as Q into V cross B dot dr? Dr can be written as V dt. Because V equal to dr dt, instantaneous velocity. So I write dr equal to V dt. Okay. Now, what is the value of this product? This part, V cross B dot V, 0. Because V cross B means force. That force is directed perpendicular to the plane containing V and B. Previously, when we draw this diagram, see, what is the angle between Fm and V? Perpendicular. So whenever you are calculating this one, V cross B dot V, the angle between in the dot product is 90. So angle in the dot product 90 means dot product will become 0. So this one immediately comes to 0. So magnetic force on a charged particle is a no work force. Magnetic force on a charged particle is a no work force. Okay. Now, if it is a no work force, then tell me, in the magnetic field, what will happen to the kinetic energy of a moving charge? Kinetic energy will change or it will remain same? In this uniform magnetic field, kinetic energy of the particle will change or it will remain same? You studied work energy theorem in work per energy topic. Work energy theorem says that work done equal to change in kinetic energy. What is work done here? 0. So change in kinetic energy will be 0. So kinetic energy will not change. So write down, according to work energy theorem, according to work energy theorem, work done by a force equal to in a uniform magnetic field, kinetic energy of a charged particle will never change. Okay. Now, what will happen to the linear momentum of the particle? Kinetic energy remain constant, then what will happen to linear momentum? Will it change due to magnetic force or not? Kinetic energy will not change. Then linear momentum. What is the relation between kinetic energy and linear momentum? P square equal to 2m into kinetic energy. M is constant, K is constant, not changing, K is kinetic energy, not changing. So P square will change? No. Then P will not change. You are eager to write that, but that is not correct. Linear momentum will change. See, don't forget Newton. So many laws have discovered by Newton and you are forgetting Newton. According to Newton's law, linear momentum is conserved only when external force is absent. Here external force is a no work force, but force is not absent. That is not correct. Force is present. Force is magnetic force, is an external force. And in presence of external force, linear momentum can never be conserved. So no work force will not tell you that linear momentum is constant or not. For linear momentum conservation, no force should be there. But there is force. Now the problem arises, kinetic energy is constant. Okay, fine. Then V will be constant, half mv square. then how momentum can change? Kinetic energy means half m, which quantity square? What? Velocity or speed? Velocity square means v dot v. There is a dot product. So essentially it is speed square. So speed will remain same, but the particle will move in a circular path. So direction of velocity vector is always changing. So centripetal force is required, and that force is provided by magnetic force. Since the velocity vector is changing, momentum vector is also changing. So linear momentum cannot remain constant. So don't forget that kinetic energy is half m into speed square. So speed is constant, but that does not mean velocity is constant. If the particle is moving with uniform circular motion, you have already studied uniform circular motion. So the motion of the charged particle in the magnetic field will be uniform circular motion. So in that the speed remain constant, but the direction of velocity is continuously changing, and for that centripetal force has to be present, and that centripetal force is provided by the magnetic force. So linear momentum will not be conserved, it will change. Okay, because change in linear momentum provides this centripetal force. So write down these points. You have written already that kinetic energy is constant. Then after that write, so speed of the particle will remain constant. Speed of the particle will remain constant, but velocity vector is changing direction. So linear momentum is not constant. Velocity vector is changing direction. So linear momentum means mass into velocity. So if velocity vector is varying, then linear momentum is also varying. So linear momentum is not constant, it will vary. Now generally when we draw magnetic field lines in the diagram, we will show magnetic field by this symbol. Now, so this means that the magnetic field is inside the board, and if it is dot, then it is coming out of the board. Again, we are using, in the slopy language we will say that magnetic field, but it's not the magnetic field. It is called the magnetic field induction or magnetic flux density. The B quantity that I have written is called the magnetic field induction or magnetic flux density. Don't write magnetic field intensity, because in this case magnetic field intensity is defined by some other vector H that you learn in magnetism in matter, that topic. So it is called, write down the name. Generally speaking, we can say that what is magnetic field, but actual name is magnetic field induction or magnetic flux density. This B. Okay, so we consider that the B is directed uniform and directed inside the board. Now we consider a charged particle is released from this portion along this with a velocity v. charge particle in this field is released along this portion with a velocity v. Then what is the direction, what is the angle between v and b? 90 degree. B is inward and v is horizontal. V is like this and b is inside. Angle between them is 90 degree. Means v and b are perpendicular to each other. So what will be the direction of magnetic force on this charge particle? Downward. See, this is v, b is inward. So place your all four fingers along the direction of v and then go in the direction of b. B should be inward. So your thumb will show the direction downward. V is there, so place all the fingers, then go in this direction towards the direction of B. B is inside, so your thumb will show the direction downward. Clear? So that is the direction of the magnetic field. Again check. This is the direction of B. I place all my four fingers of the right hand along the direction of B. Then B is inward. V cross B. Thumb will show downward. Okay. So magnetic field force direction on this charge particle is in the downward, and it's a no work force. So what will be the trajectory of this particle? Circular. So this particle will move like this. Okay. So the magnetic force here is directed along this Fm. It will be Fm. Fm is directed towards the center of this circle, radially inward, means it provides the centripetal force. Okay. Now then we can write that what is the magnitude of this Fm? Q, what happened to this one? VB, QVB only. Sin 90 will come, sin 90 will be 1. So this force on the charge particle will be QVB and directed towards center of the circle, and the particle is moving with a speed v in a circular path.